has an important common feature with the first lecture, because both of them tell us about the loneliness of scientific disciplines today. In this, what I mean is, I mean that their incapacity to look around to fields which are very related to their field and to the need to interact with all these fields. I called this lecture "Two Neighbors Ignoring Each Other." As a matter of fact, in my preceding lecture could be called 15 people, 15 neighbors ignoring each other. These two neighbors are the field of infinite words and the field of formal languages. And you can see from the beginning why they ignored each other a very long time. Formal language and infinite words are two fields which, despite their strong connections, ignored each other to a large extent. Maybe I should to recall you, these are very simple ideas. What is an infinite word? No, it is an infinite word as infinite sequence on a given finite alphabet. Clear, what does it mean? What is a formal language? This is a collection, a set, finite or infinite, of finite words on a given finite alphabet. So you have finite words on a given alphabet. Each word in English is a word on the alphabet of English, no? And their set is a formal language. It is clear that they are, even by their definition, they are very near each other. Because if you have a formal language concatenating all the words in the language, you get an infinite word. And if you have an infinite word, any prefix of this word is if you take all prefixes of an infinite word, they form a formal language, because an infinite word has infinitely many prefixes, so they are very related. But reasons for this situation, I give several reasons. The sources of their problems are different. Formal languages, they were inaugurated mainly by Noam Chomsky in the 50s of the past century, and then we had also, so the sources are linguistics, logic, computer science, combinatorics, with Axel Thue at the beginning of the past century. While for infinite words, sources are completely different. Dynamical system, discrete dynamical systems, ergodic theory, number theory. And you see, this is what happens, unfortunately, when people begin to be trained in a definite field. It is very difficult later to invite them to look beyond the field where he was trained. Second reason, the length of words, one of the basic parameters involved in these fields, was never the central concern of a systematic study, but only an auxiliary tool. Third reason. The asymptotic behavior of various parameters involved in the above fields, the only one able to account for the dynamic aspects was in most cases neglected. And this is also related to the ignorance in analysis of many computer scientists. Most computer scientists were educated only in discrete mathematics, while here you need to understand the asymptotic behavior. So it means the behavior of words in a language when the length of these words is increasing. Infinite words were considered by Axel Thue at the beginning of the past century, but it was a very isolated thing. But the real act of birth, I think, should be located in Morse and Hedlund 1938 paper, where there is a fundamental result characterizing periodic infinite words, ultimately periodic infinite words. And he gave 4 conditions which are pairwise equivalent. The word is ultimately periodic. Well, the terminology I use here is not the terminology used in 1938. At that time, the word complexity did not exist. But I use this terminology. The complexity function, this means a function associated to each n, the number of factors of length n in the respective infinite word, is bounded. This function, this means there is a k which is larger than fn for any value of n. Third condition, there exists an integer n strictly positive for which we have this strict inequality, k being the cardinal of the alphabet. And the fourth condition, there exists an integer n such that we have the function fn, which is a sequence, becomes stationary. At some moment, it becomes stationary, all terms are equal. You can understand the importance of periodicity. It is the simplest, the smallest complexity you can imagine for an infinite word. You cannot imagine something simpler than periodicity. So this is the lowest possible complexity. And periodicity is also interesting because its negation gives the concept of a primitive word, which is very important. So, what follows from this theorem is something very interesting. it follows that the lowest possible complexity for an infinite word which is not periodic is in the case when you have this relation for all values of n. And these words are said to be Sturmian words, according to the name of Sturm. So this corresponds to the lowest possible complexity which is not bounded, because if it is bounded, it gives periodicity. And you can see now already the strange thing, what does it mean, the lack of communication between people working in infinite words and people working in formal language. You know, the same condition under number 2 was considered for formal language only in the 90s of the past century, ignoring completely that a similar condition was already considered for infinite words in 38, and it was introduced in 93 by Paul and Saloma under the name of slenderness. This means a formal language is slender if the function giving for each n the number of words in language of length n, this function is bounded. This is a slender function. And a very rich literature was published in this respect. Now, remaining now at infinite words. It was an interesting transfer from analysis into discrete mathematics of the concept of almost periodicity. It was introduced in analysis by Harald Bohr, the brother of Niels Bohr. And I tell you the anecdotic fact that Harald Bohr was a member of the football team of Denmark at the football championship in 29. And this is the definition and analysis of almost periodicity. For a continuous function f, it is almost periodic. For any epsilon positive, there exists a strictly positive delta epsilon, or such that any real compact interval of length delta epsilon contains a number tau epsilon with this property. And you see that it is clear that it is an extension of periodicity. And then we get the discrete variant of almost periodicity, I will tell you now in several variants. What is interesting? In combinatorics and computer science, the terminology almost periodic is no longer used. They replaced it by uniformly bounded. Uniformly recurrent. And so the links with the almost periodicity in analysis was lost. Look, first variant. I will give you 5 variants of almost periodicity in discrete case, but all these 5 variants are equivalent, any 2 of them, but unfortunately you will find one variant in some places, another variant in other places. None of them will tell you about the equivalence with other variants. For instance, the variant you find in Jacobson-Keene, the infinite word on the alphabet is almost periodic. For any finite factor x, there exists a decomposition in words which are of the same finite length, and each of them includes a copy of x. Obviously, it is an extension of periodicity. You get periodicity in the case when all these words of finite length are the same word. The variant considered in ergodic theory by Furstenberg, 81. The word is said to be uniformly recurrent if for each positive integer k there exists a constant nk, such that if x is of length k occurs as a factor of the infinite word, then it occurs in any factor of length nk. The variant considered by Ehrenfeucht, Lee, Rosenberg, 75, and Alush, 94. The word is uniformly recurrent if any finite factor x of the word occurs infinitely many times, and the gaps between consecutive occurrences of x, of the word, not x, x is w, are bounded. Maybe this is the most intuitive. And the variant considered in 98 by Aldo De Luca, Stefano Mauricio. The word is uniformly recurrent when every finite factor of the word occurs synthetically. This means there exists an integer k such that in any factor of the word of length k, there is at least one occurrence of x. And the fifth one, the infinite word is minimal if there exists no other infinite word on the same alphabet such that every factor of the word v is a factor of the word w. And the basic fact is that all these 5 variants are pairwise equivalent as different aspects of almost periodicity. Now you see the shortcoming. Why it is important, you can see the importance of terminology. Because if you use the term almost periodic, you have immediately a natural question. Well, we define almost periodicity, but we should not define also what does it mean an almost period. Like for periodicity, we define periodicity with a corresponding concept of a period. And the sad fact is that we don't know how to answer this question. There is no concept of almost period staying in respect to almost periodicity like period is in respect to periodicity. And anyway, the fact that the same concept came from completely different directions shows its importance. But the fact that each of these directions ignores the other directions shows a very unpleasant situation where you cannot take advantage of the other approaches. Now you see, I told you about, I will go between infinite words of finite formal language and back. Slenderness. As I calling slenderness now also the property for infinite words, you see, it was introduced for infinite words almost 60 years before its introduction for languages. And the problem was to transfer to language of Morse-Hedlund theorem characterizing periodicity. And you see here what happens. A language for which the complexity function is bounded is of this form. You have it here. Here is the description of xi, y, z, y, I. So it shows the degree in which the language is periodic. Now, in the period from 1980 to 1990, some papers on slenderness, without the use of this term, were published by a lot of authors, Rosenberg, Shalit, and more recently, Demesi, Honkala, Ilie, Masami, Tokudlek, Nishida, etc. And in this way, we began to ask about general transfers from infinite words to language and back. For instance, we have the concept of a Sturmian word. What could mean the concept of a Sturmian language? First of all, let us compare the complexity function for infinite words and the complexity functions for formal languages. If you define the complexity function for a formal language as the function giving for each n the number of words of length n in the language, I have to tell you that the characterization, the necessary and sufficient conditions for a function of positive integers to be a complexity function is very simple and completely known. I will not insist, this problem is solved. In contrast, the characterization of the complexity function for infinite words, I repeat, this means the function giving for each n the number of factors of length n. This problem is extremely difficult. We know some necessary conditions, but we are very far from answering, from having a necessary and sufficient condition characterizing so the complexity function of an infinite word. And we will see why. So, the contrast I put there. Now, I recall you, the language is slender if L, F, L is bounded. L is K slender if L, the complexity function is not larger than k. The language L is thin if it is one slender. This means no two words have the same length. This means the language is thin. Now, this helps us to give conditions for a language to be the language of prefixes of an infinite word. Here are the conditions. You can read them here. If PL is thin, if PU, here is a mistake. Instead of L, you should have U. If the language of prefixes is thin, and if any strictly positive integer is the length of some word in L, then there exists an infinite word such that PU equal L. Conversely, if L is the language of prefixes of an infinite word, then L is thin and for any strictly positive integer is the length of a word in L. Warning: the language PL of prefixes of words in an arbitrary language is not always thin. Now, back to the complexity function of a language. Can it be considered? The problem is now, if it is right to call this function, giving in a formal language for each L the number of words of length n, if it is right to consider it as a complexity function. This means if it really accounts for the complexity of the language. And the answer is negative. In order to keep the similarity between formal language and infinite words, we have to pay attention to the following thing. As a very simple thing, you may say trivial. Trivial but essential. It is the following fact. You have a factor of an infinite word. Any factor of a factor is still a factor. This property called heredity is no longer valid for words in a language. From the fact that X is a word in the language L, it does not follow that any subword of X is still a word in the language L. And this invalidate the capacity of FLN to function as a real complexity function. Then, how to bridge this gap? Very simple. Replace small fl by big FL. This means big FLN is the number of factors of length n of words in L. So you see the difference. Instead to take the number of words of length n, I take the number of factors of length n of words in L. And with this modification, we have a real similarity between the behavior of formal language and the behavior of infinite words. look, I introduce the function SU. This means a set of lengths of factors of U. Obviously, SU includes all positive integers, because in an infinite word you have factors of any length. So infinite word is complete in length. Fun, now the function fun, the cardinal of factors of length n of u, it is a complexity function. And as I told you, no characterization of fu exists so far. This set, big Fu, including all values of the complexity function for 1, 2, 3, etc. value of argument, defines a total complexity. The description of Fu for various classes of infinite words is the object of many current investigations. I will go further, and now I will give you a picture to understand the situation of infinite words before asking for a possible correspondence to language. You have the infinite words. As a part of them, you have the recurrent words. This means words in which each factor appears infinitely many times. And look here, something very interesting. Almost periodic words are all recurrent, but the converse is not true. But look there, among recurrent words, there are two very interesting classes. The class of disjunctive words, this means words in which every factor, not only every factor, but any possible finite word, irrespective it is or not a factor of the infinite word, appears as factor infinitely many times. This is a disjunctive word. And as a particular class of disjunctive words, you have the random words I told you about in one of my preceding lectures. So you can understand, because in the everyday language, random is sometimes considered equivalent with arbitrary, at random. In mathematics, these two words, arbitrary and random, are completely different. Words, that I say all infinite words, this means that arbitrary infinite words. But random words are a very special case of infinite words. Any random word is disjunctive, any disjunctive word is recurrent, but in each case the converse is not true. So you can understand the paradox of the situation, that when we learn these things, you begin to doubt whether the definition of randomness is the right one, if it is has so many constraints. But anyway, you see two ways to look at infinite words, from the top and from the bottom. From the top, you have infinite words, recurrent words, disjunctive words, random words. From the bottom, you have periodic words, ultimately periodics, Sturmian words, Delphi's word I did not define, quasi-periodic word I will define, almost periodic words. But these two hierarchies, one from the top, the other from the bottom, cannot be bridged. You cannot bridge them. What happens between them, we don't know. Now, I have to tell you, because I did not tell you what does it mean a quasi-periodic word. Very important, if you recall from my preceding lecture, quasi-periodic words were introduced in the study of DNA in a very important paper. And what is nice, another source of quasi-periodic words is musicology. So it is not very nice to have a concept, these two sources, music and DNA. And by means of it, we can speak about the music of the DNA. I will tell you what does it mean. For finite words, quasi-periodicity introduced in the study of DNA by Carlin, Morris, Gandon, Long, Proceedings of the Natural Academy of Science, USA, 88. A very long paper. And in musicology by Crawford, Iliopoulos, Raman. Computers, there is a journal called Computers in Musicology. In 98, very late. What does it mean, the finite word of the alphabet is quasi-periodic, if there exists a proper subword, y, such that any position in x is within an occurrence of y. For instance, I think I have to write, it's easier to see. This word. Clearly it is not periodic, but it is quasi-periodic. Why? Look, the derivation says there is a proper subword. In our case, it is ABA, such that any position in the word is within an occurrence of this. Any position, no. These are two occurrences of ABA, this and this, and any position is included in one of them. And then you can see also the geometric difference between quasi-periodicity and periodicity. In periodicity, you have this situation. In quasi-periodicity, you may have also you see, overlap. You have also overlapping, not only concatenation. This is the difference. And then, starting from this situation, I said it would be very interesting to transfer this concept to infinite words. In infinite words, it is simpler, because you say, what is an infinite, quasi-periodic infinite word? Is an infinite word for which there exists a factor such that any position in the infinite word is included in an occurrence of this factor. And obviously, look, here is an example. You can, the rule of formation. You have ADA power n dA, ADN power n plus 1, for n going from 1 to infinite. it has ADA as quasi-period. But it happens the following thing. You have, like almost periodicity, quasi-periodicity is an extension of periodicity. But it can be proved that quasi-periodicity is not comparable with all other types of infinite words I told you about. Not comparable with almost periodicity, not comparable with recurrent words, etc. But it happens something very interesting. As soon as the number, you see the advantage of quasi-periodicity in respect to almost periodicity. I told you, for almost periodicity, we have no concept of almost period. For quasi-periodicity, we have. It is just this factor, which is containing any position, is called a quasi-period. And it happens that the most interesting quasi-periodic infinite words are those having infinitely many quasi-periods. And if they have infinitely many quasi-periods, they are obligatory uniformly recurrent. This means almost periodic. So almost periodic includes quasi-periodic as soon as the number of quasi-periods is infinite. So I come back to the so you understand now better this, but in this picture there are many things we are not able yet to answer. Relation between quasi-periodic and tertiaries, for instance, or for Sturmian, with Sturmian. We don't know how to answer this. But now, what we can answer go back to the interaction between infinite words and finite formal languages. Here, for instance, you have some pairwise equivalent conditions for an infinite word to be slender. The infinite word is slender. The language, big F, U, this means including all factors of U, is slender. U is ultimately periodic. Then you have this inequality for some positive integer M. And then combining strong slenderness with Morse handbook, strong slenderness, this means for formal language when we use the new complexity function I introduced. You have this equivalence. For the language of prefixes of an infinite word, you have equivalence between L context free, L regular, U ultimately periodic, L strongly slender. And another condition, any long enough word in L has a cube as a suffix. There are interesting things that I cannot go there in. By using the parameter called the topological entropy, defined as this limit, where the existence of a limit follows from the additivity of the function log. Open problem. What about the topological entropy of a language L? What about this limit? We don't know. And now here is the paper where we give the way to understand the concept of a Sturmian language, because the concept of Sturmian language did not exist. It was only Sturmian infinite word. Main idea, the complexity function. What I told you, what is complexity function? Following the similarity with infinite word, we prove that the complexity function FLN of L is either bounded, and in this case L is said to be periodic, or we have this inequality for any n. It follows that for non-periodic languages, the smallest possible complexity is obtained when we have for any n this relation. And we have immediately an example of a Sturmian language, the well-known language formed by a power m, b power m. It is Sturmian. You have always f n equal n plus 1. And we describe also the periodic, the structure of periodic language, pointing out the way the attribute periodic is added here, and we characterize Sturmian language as a set of factors of a Sturmian infinite word. There is also a proposal for another complexity function proposed by Nakashima, Tamura, and Tetsuzo. Instead to count the number of factors of length n, they count the number of factors appearing infinitely many times. Factors of length n appear infinitely many times. And the maximality of this type of complexity is implied by the learned from a Horov-Chaitin randomness. But we don't know yet how to answer what could be the type of this type of complexity for a language. Well, there is also a final question. To what extent is this typology of infinite words correlated with the typology of formal language? To each infinite word one can associate the language of its factors or the language of its prefixes. To each formal language one can associate an infinite word obtained by concatenation of all words in the language. But here a very interesting question appears. A natural order could be the lexicographic one for words of the same length, while shorter words would be anterior to longer words. One can expect that the asymptotic behavior of this infinite word is in some respect independent, or at least partially independent, of the order of concatenation. This is a question we don't know yet to answer. But before I put an end, I have to make a correction to some point of my lecture last week. It refers to the fact, you remember when I defined analytic, speaking about mistakes. Analytic, speaking about mistakes, I had to expect to commit a mistake. And I committed a mistake. The mistake was the following. I spoke about analytic and projective sets. The correct definition of them is the following. A set is analytic, is a continuous image And projection, I consider them, is a particular case of a continuous image, obviously. This is a definition of analytic set, the continuous image of a Borelian set. The definition of the hierarchy of projective set is the following. It happened that the complementary of an analytic set is still analytic only when the set is Borelian. So you see, Borelian sets are included in analytic, and it happened that the projection of a Borelian set on the straight line can no longer be Borelian. The converse is not true. But when you take the complementary of an analytic set, it is analytic only if it is Borelian. So, when you move to complementary of analytic set, usually noted by CA, they are a new class in respect to both Borel and analytic. And then, if you repeat these two operators, you alternate them, takes the complementary, takes the continuous image, then you get the hierarchy, the infinite hierarchy of projective sets, which is a very deep idea in topology. This was my correction, and at the end I want to thank you very much for having the patience to listen to me, and especially I thank Professor Israel for inviting me for these lectures, and I hope to continue to interact with you in this respect when my lectures will be on the site of Brown University, and to receive more questions, remarks, comments and criticism from members of Brown University. Thank you very much.
Thank you.